Here we have an op-amp that has a feedback loop to it, and so if it has a negative feedback loop, then the op-amp should be in the linear region, and that tells us that the voltage at the two terminals should be the same. Here the non-inverting terminal is connected to ground. This is a 0 because this is our ground, and so it tells us that this other terminal here should also be a 0, and in fact that is going to extend to everything else. Then if we want to consider the currents that are flowing into these terminals, remember that those currents are assumed to be 0, that we have a very large input resistance to our op-amp, so there's no current flowing. So we do have a couple other currents that are going to flow. We have currents flowing from different nodes. I'll call this IA and IB and IO. And then notice here, because of our voltage source, again, we have a voltage source, we have ground. If this is 0 and we go up by VA, our voltage here should be VA. If I'm at ground here and I go up by VB, my voltage here should be VB. And then my output voltage is measured relative to ground, so this should be my output voltage at that node. And so I've got 3 different currents flowing into this same node. This node that is at 0 volts is at ground because it's connected via the op-amp, and so I can go ahead and start writing a KCL equation for that. Then I can write each I can rewrite each current in terms of a voltage difference and a resistance. Now here we want to find V0 for a value of VA and VB. We could plug those in right now, but later on we're looking for the range of VA for a given value of VB, or the range of VB for a given value of VA. So it seems like it would make more sense to go ahead and leave it algebraically now, solve for V0, VO now, and then we can plug in values later, however we like to. So these values are positive here. They'll become negative when I move them across the equal sign. And I'll multiply through by 250k to cancel out the denominator to indicate V0 by itself. So what we're seeing here is that V0 is going to equal So notice here what we found for V0 is the feedback resistance divided by RA for the amplification of VA, and the feedback resistance divided by RB for the amplification of RB. Right, we've got this term here is that guy, and then we've got this term is right there, and this term is right there. And then we can go ahead and simplify that as well. V0 is equal to negative 50 VA minus 10 VB. And once we have this relationship here, this relationship is fixed. As long as we're not changing any of these resistances, we're not changing the setup of the circuit at all, this equation is going to be the same. And if we change the inputs VA and VB, then we're going to get different output voltages as a result. But we can go ahead and deal with those. So after finding the equation for VO, we really just have to plug in for VA and VB to find these different values. So for part A, we want to find VO if VA is 0.1 and if VB is 0.25. And so we can simplify that, and we get that the output voltage is negative 7.5 volts in that case. And we check that negative 7.5 volts is between the supply voltages it is, and so that must be our answer there. The second part, we're asking if we fix VB, we want to know how large VA can be before we reach saturation. So in that case, we're fixing VB at 2.5, and we're leaving VA as a variable amount. And we saw that if VB is 2.5, then that term is negative 2.5. And what we want to do here is we want to avoid saturation. Well, if we want to avoid saturation, that means that VA can be whatever it is, so that VO falls between the supply voltages. So in this case here, VO has to be between 15 and negative 10. And so I can add 2.5 to either side. And I can divide through by negative 50. Remember, when you divide by a negative value, you have to reverse the direction of your inequalities. And we end up with VA having to fall in the region between 0.15 and negative 0.35. And so if we're interested in what is the largest value VA can be, well, the largest value is at the top end of that range, which is 1.5. We can do the same thing for VA. If we fix the value of VA, we know that if VA is 0.1 times 50, we get a factor of negative 5. And again, we want to avoid saturation here. We can change VB, which will change VO, but VO can be whatever it wants to be as long as it's between those supply voltages to avoid saturation. And so here, I have a range of values for VB. If I want to know how large VB can be, that's the top end of this range. That would be 0.5 in that case. For the last part, we're asked to repeat all of this, but with the polarity of VB reversed. What this means in practice is we want to get rid of the current polarity of VB, and we want to reverse it so that it points the opposite direction. What that means in practice is this is 0. We're going down by VB, so the voltage at this node now is negative VB. We can write our KCL equation just like we did before and analyze the circuit just like we did before. The voltage at that node is now negative VB, but the calculation is just exactly the same. And you can see here what will happen is if we solve for V0, we'll end up with negative 50 VA, and it will be now plus 10 VB. So it's the exact same equation that we had before, but now we're just making it a plus VB. And now if we want to find VO given these values, we still have the same value of VB. The polarity's just changed, so now this is at negative 0.25 instead of positive 0.25. We've accounted for that in the equation. This VB here is the amount, and we accounted for the polarity with the negative sign already, and so we can just plug the values for VB into this equation. So for example, for the first part the second time around, and we get negative 2.5 volts this time. You can do the same thing that we did in the other equations as well. We can fix VA or VB, and then to avoid saturation, we make sure VO is falling within the span of the supply voltages. So again, we have the same value here, and we know that this has to be between the supply voltages. And so if you plug in VA or VB, you plug that in here and you solve for the other one, and you make sure you stay in that range so to make sure that you are avoiding saturation.